Welcome to next lecture on torsion of non-circular shafts, part 2. Torsion of non-circular shaft. So what we have seen in previous lecture is displacement field. Then we derived strains from the displacement field. After that we moved to evaluate stresses, and then we derived equations of equilibrium. From equilibrium equation, what we derived is Laplace equation del square W is equals to 0. Now in today's lecture we'll try to solve this equation and evaluate W by Prandtl's stress function. So before we move to Prandtl stress function, I need to show how the shear stresses or stress vectors are acting on the cross section of shaft. For example, consider a general cross section area with coordinate system shown as x, y and z coming out of plane. So now if you consider this shaded area here, if this is the tau xz component acting and this is the tau yz component acting. So let me draw this area in 3D space. So let's consider this. So shaded area will be like this on the shaft in 3D, and the normal to the area n bar will be coming out of the plane like this. So if z is this direction and this is x, this is y, then this n has direction cosines l comma m comma n, and as this is coming out of plane and perpendicular to the y and x, we can say that this is 0, 0 and 1. Once we know the direction cosines for this area, shaded area, we can write the stress vectors using Cauchy's stress formula. Now Cauchy's stress formula is sigma ij n j, which is equal to SI, stress vector in ith direction. So for Sx, we'll write L into sigma x plus m into tau xy plus n into tau xg. So here L and m are 0, this is also 0, this is 0, and n is equals to 1. That means Sx is equals to tau xg. Similarly, y component of stress vector, which is given by Sy, is equal to L into tau yx plus m into sigma y plus n into tau yz. Here this is 0, this is 0, this is 0, this is 0. So sy is equals to, and n is equals to 1. That means sy is equal to tau yz. Similarly, we can derive for traction in z direction. Stress vector in z direction can be derived from L tau xg plus m tau yz plus n tau n sigma z is equals to 0. So this is 0, this is 0, and this one equals to 1, but this is 0. So here z is equals to 0. Now again consider same area, and now we know that tau zx and tau zy are acting on the area dA. So this is the area dA. Let's approximate this boundary by straight line and then draw the perpendicular to it. So on this boundary, this is the vector n, and for which direction cosines are L, M, 0, as this n vector is perpendicular to z bar. So it is perpendicular to z direction, hence we are taking direction cosine in that direction as 0. So let's find out the force resolution in the direction of n. What we can write is L into this direction dA into tau zx plus m into dA, which is the area, and into shear stress component zy, which will be equals to tau zr into dA. Now this tau zr is acting in this direction, and if this is the r direction, then this component is zr. Therefore what we can write is L tau zx plus m tau zy is equals to tau zr. Okay. So similarly, we'll see another area. Let's consider some small area here on the outer boundary of the shaft, and the perpendicular to this shaft will come as n bar, and now this n bar is perpendicular to the z, so we can write direction cosines as lm0, and again we'll use Cauchy stress formula. So L into sigma x plus m into tau yx plus n into tau zx. So now here this is 0, this is 0, this is 0, which is equal to 0. Sy is equals to L into tau x y plus m sigma y plus n tau yz, which is equals to again this xy 0, this 0, n is 0, so it is 0. So sz is equals to L tau xg plus m tau yz plus n into sigma z. This is 0, this is 0. Now on the outer boundary there is no traction acting, so this component is 0, and we can see that this term goes to 0. Hence we can say that component tau zr is equals to 0, which implies that shear stress in radial direction is 0. Let me draw the diagram again. This is x, this is y, this is z, and let's draw an element in the radial direction. So this tau zr, which is equals to z, and this rz is equals to z, which we have proved from the above three considerations. First one is like this, then second just considering the boundary, and third one boundary element on the shaft surface. Coming to next stage of this torsion problem, here we will try to derive the equation for warping function. So we'll try to solve for warping function. So how to get this, the warping function w, and for this we'll move to Prandtl stress function. Method. So here tau xg is assumed to be function of p, which is given by derivative of p with respect to y, and tau yz is equal to minus dou p by dou x. So here p is Prandtl's stress function. We know tau xg is equals to g into dou w by dou x minus theta y, which is equals to dou phi by dou y. Tau yz is equals to g into dou w by dou y plus theta x, which is equals to dou phi by dou x minus. If we differentiate first equation with respect to y, so dou square phi by dou square dou y square is equals to g into dou square w by dou x dou y minus theta. And if we differentiate second equation with respect to x, then dou square p by dou x square is equals to g into dou square w dou x dou y plus theta. Now subtract this equation P from A, so we'll get dou square P dou x square plus dou square P dou y square, which is equals to, okay, I missed a G here, which is equals to minus 2g theta. This is our next equation in terms of Prandtl stress function, and it is nothing but Poisson's equation, and theta is angle of twist per unit length. G is shear modulus. Here again we'll consider the boundary. Say this is x, this is y, and this is the boundary, and this is your point P, and this is your point Q. So point P to Q, torsion direction is given by this arrow, and let's approximate this by straight line perpendicular to this. PQ is given by n bar, which is L comma M comma 0. This angle is alpha. This distance is minus dx. This distance is dy. Okay, so as this angle is alpha, hence this is also alpha. Let's consider PQ is equals to ds, small elemental area, small elemental length on the boundary of cross section ds. So we know from this equation that L into tau xg plus m into tau yz is equals to 0. L into tau xg plus m into tau yz is equals to 0. And tau xg is given by dou pi by dou y plus m into minus dou pi by dou x, which is equals to 0. Let me draw this diagram again. So here this is P, this is Q, this is alpha, and this is minus dx, this is dy. Okay, so L is equals to cosine of alpha, and m is equals to, so let me draw n. So this is alpha, this component is L, this is m, so this is 90 minus alpha, so m is equals to sine alpha. And from this diagram what we can say that cos alpha is equals to dy by ds, and sine alpha is equals to minus dx by ds. Now putting values of L and M in this equation, what we can write is dou phi by dou y into dy by ds plus dou phi by dou x dx by ds is equals to 0, which is nothing but the total derivative of phi with respect to s is equals to 0. Hence what we can say that if we move along the boundary, the derivative of p is 0 along boundary s or ds. Hence this implies that phi is constant on the boundary of the shaft, and normally phi is equals to 0 is assumed. I think this is enough for today's lecture. In next lecture we'll see how this shear stresses acting on element will affect the moment resistance, and will relate this to torque applied T and tau zx and tau yz will be used for the derivation of T, and then we'll correlate this T with phi. So see you in the next lecture. Thank you.